Hello. In this video we're going to go over the combined gas law. So after I talk a little bit about the combined gas law, we'll go through the textbook problems in the Chem 1-2 book, page 391, numbers 25 through 33. So, what is the combined gas law? Well, it's basically it's a single law that combines the three gas laws that we've talked about, which are Boyle's law, Charles' law, and Gay-Lussac's law. So you really don't need to memorize any of those individuals as long as you know P1 V1 over T1 N1 equals P2 V2 over T2 N2. That's the combined gas law. Now, in most of the problems we're going to work through now in Chem 1-2, we're going to be holding moles constant. We're not going to throw you anything where the moles change. So most of the time, unless it's specifically noted otherwise, unless it's noted that the moles are changing, we can even eliminate N1 and N2. And in fact, if you Google combined gas law, this is what you're going to see. Very rarely do you see the N1 and the N2. So you should know it both ways, but be more familiar with this, because this is kind of the standard chemistry combined gas law. Okay? Now what's useful about this is if any of these three parameters, pressure, volume, or temperature, are held constant, you can just eliminate them. So let's say we're working with a container with a gas in like a steel tank. So when I think a steel tank, what's going to be held constant? Well, the volume. Well, in this case, you could just cover up V1, or remove it, cover up V2, remove it, and now you just have these four terms here. Let me rewrite them. Same thing applies for any of the others. If pressure is held constant, think of a balloon that's really able to move. You can eliminate P1 and P2 and you just have the V and the T left. Or if temperature is held constant, you can eliminate them. So if anything is held constant, you can eliminate it, which is essentially what we're doing with moles, because technically N1 and N2 are here. So anytime I use this formula, I'm assuming that my number of moles is held constant. Now, other times, nothing is going to be held constant. We'll go through some of those problems. So that would be like if I give you an initial set of pressure, volume, and temperature, and I say, well, what if I change the pressure? What if I change the volume? What would the new temperature be? Or something along those lines. Well, in that case, I'm going to give you 5 conditions. You solve for the 6th one. So this just requires a little bit of algebra. So a few things we need to know how to do before we start. First, you need to know how to rearrange this to solve for any one of these 6 variables. So you should be able to isolate any of these. And as we go through the problems, we'll go through some examples of that. Second, you need to know your pressure unit conversions. Now in Chem 1-2, specifically for Chem 2, we say you need to memorize 1 atm equals 760 millimeters mercury, which equals 760 torr. Now remember, this is true by definition, so it's infinite sig figs. So if the problem says you have a gas at STP, don't limit yourself to 1 sig fig or 2 sig figs because of that. This is assumed to be true. So if something's at STP, that part of the problem is infinite sig figs. So if I give you a gas pressure, let's say I tell you pressure 1 is 523 torr. If you need to answer an ATM, which sometimes you'll have to do, you need to be able to convert this. So with conversions, we use our good old-fashioned conversion factors. In this case, if I want to go from torr to ATM, I'm going to use 1 ATM equals 760 torr. So my setup's going to look like this. 523 torr times 1 ATM over 760 torr equals, and then we get our answer that way. 523 divided by 760 is 0.688. Now I chose 3 sig figs because of this. I didn't cut myself to 1 or 2 sig figs because this is true by definition, so that's my new pressure. So you should be able to do conversions with any of these units. And in fact, in this particular set of problems, it gives you other units like pascals and kilopascals. So let's actually add on to this. You should write this down. It should be in your notes already. But this is also going to be equal to, these are all, this equals that, equals that, equals this, which is 101,325 PA, which is pascals. And that's also just going to be equal to 101.325 kilopascals. Okay? So you should have all of these down. Memorize the top 3. These 3 just for the use of these problems you should know. This is, of course, equal to a whole lot of other units. 14.7 psi is probably the most common that you should know. So that is basic temperature conversions. The other thing you're going to have to know for this type of problem is STP. STP stands for standard temperature and pressure. It's basically a set of conditions. So standard temperature is 0 degrees Celsius, which is the same thing as 273.15 Kelvin. Standard pressure is 1 atm. Okay, now it's 1 atm, which means it's also 760 mmHg, 760 torr, 101,325 pascals, 101.325 kilopascals. So it's 1 atm in all of the equivalents. That's STP. Okay, and really the last thing, and I kind of should have mentioned this earlier, anytime we use temperature in a combined gas law problem, you have to use Kelvin. So temperature must be in Kelvin. Now the reason for that is that Kelvin is the absolute temperature scale, meaning it truly reflects the amount of heat something has. For example, if it's 30 degrees Celsius today, which is a warm day, and it's 15 degrees Celsius tomorrow, did it get half as hot? I mean, mathematically, yes, 30 to 15, it got half as hot. But in terms of the actual heat of the molecules, did it get half as hot? No, because Celsius, just like Fahrenheit, are just human-created scales that fit our lives very nicely. They don't really represent the actual temperature. Kelvin does. So if it goes from 15 Kelvin to 30 Kelvin, then it has, in fact, doubled in temperature. So the whole idea behind the combined gas law is that if you double the temperature, your pressure is going to double if volume is held constant and number of particles held constant. Or in a, let's say in a flexible container, if you double the temperature or have the temperature, you're mixing up what's that? Flexible container, so the volume. In a flexible container, if you double the temperature, the volume's going to double, or if you have the temperature, the volume's going to halve, assuming the other two constants or the other two parameters are held constant. So you have to work in Kelvin. So you have to know that to go from into Kelvin, it's going to be your degree Celsius plus 273.15. Now, just as a little shortcut here, if I tell you something like, let's say 31 degrees Celsius, if you add 273.15, that's going to give you, what, 304.15? But you're going to actually report this with how many sig figs here. We don't really think about sig figs, we think about decimal places. So this is 0 decimal places, or in other words, rounded to the nearest whole number. So this is going to be 0. So that's just going to be rounded to 304 Kelvin. Notice, if I don't give you a point something something, you're not going to use the 0.15 anyway, so you can just add 273. So in other words, if I give you a whole number for your temperature, just add 273. It just saves you some time. If I told you 31.00 degrees Celsius, well now, since I told you 2 decimal places, you need to tell me 304.15 Kelvin. Okay? Alright, let's go through some sample problems. So, first one, flask containing 155 centimeters cubed of hydrogen was collected under a pressure of 22.5 kilopascals. What pressure would have been required for the volume of the gas to have been 90.0 centimeters cubed, assuming the same temperature? Okay, let's write down what we're given. So we have 155 centimeters cubed. That's going to be our initial volume, V1. Under a pressure of, so P1 is 22.5 kilopascals. What pressure would have been required, so P2 is going to be my question mark, or you can even say X, for the volume to have been 90.0. So V2, my new volume, is going to be 90.0 centimeters cubed. Notice it says temperature is held constant, same temperature. It's also assumed that number of particles, or moles, are held constant. You don't see anything here about changing moles, so we can leave N1 and N2 out of the equation. So when it comes to writing our formula, I always just write the entire thing and then cross out. But if you're kind of intuitive enough to say, well, look, T1 and T2 are going to be constant, you don't even need to write them, that's fine. But I'm going to write P1 V1 over T1 equals P2 V2 over T2. And now I'm going to say, notice temperature is held constant, so we're going to divide it like this. Okay? So P1 V1 equals P2 V2. This is actually known as Boyle's law. We are solving for P2. Now, at this point, you can plug your numbers in and just get your answer. But I always prefer and advocate for you guys to rearrange first. Get this by itself. Isolate the variable you're looking for, because then your units are going to cancel out nicely. You're much less likely to make a mistake if you rearrange this first. Trust me, I've seen a lot of students make a lot of mistakes, and you make a lot fewer mistakes if you rearrange first. So how do we get P2 by itself? Well, we need to divide both sides by V2 to get this out of here. So V2 is going to reappear underneath here. P2 equals P1 V1 over P2. Let's plug in our values and units. So 22.5 kilopascals times V1, which is 155 centimeters cubed, divided by P2. Oh wait, I'm solving for, whoops, I divided by the wrong one. I'm sure you caught that though. So we're looking to solve for P2. I needed to divide by V2. Sorry. Okay, divided by V2. So V2 is going to be 90.0 centimeters cubed. Okay, let's check our units. Centimeter cubed cancels centimeter cubed. What unit is left? Kilopascals. Does that make sense for pressure? Yes, it does. So always rearrange first and check your units. Now before we solve, some people have said, well, don't you have to convert to atmospheres in order to use this equation? No. Unless the problem tells you what pressure unit to report, which in this case it doesn't, whatever pressure unit you plug in as P1 is going to come out as P2. That's fine. Same thing for volume. Whatever volume unit you plug in for V1 is going to come out as V2. Now if you're going to use V1 and V2, these units have to match, and if they don't match, you're going to have to do a conversion. But really the only unit that has to happen in these problems is Kelvin. Your temperature has to be in Kelvin, no exceptions. Pressure can be anything, volume can be anything. Let's solve. So 22.5 times 155 equals, divided by 90 equals 38.75. Now for sig figs, I'm going to look at what I plugged in here. 3 sig figs, 3 sig figs, 3 sig figs, 38.8. I'll write it. 38.8, and my unit is kilopascals. And really the last thing you want to do in a problem like this, especially if it's on a test or quiz, is take 15 seconds and just think, does this make sense? Let's read the problem. So you have a flask with 155 centimeters cubed at this pressure. What would the new pressure be if it's 90 centimeters cubed? So think about this. The container started at 155, shrank down to 90. If you shrink a gas, what's its pressure going to do? Well, pressure is going to increase. You're giving it smaller area for those force particles to hit, so the pressure is going to increase. So does it make sense that the pressure went from 22.5 to 38.8? Yeah, makes sense. So we can move on. 26. Gas has a volume of 450.0 milliliters. If the temperature were held constant, what volume of the gas would the gas occupy if the pressure were doubled and reduced to 1/4? So this is kind of like a just thinking type question. We don't even really need to do an entire equation for this. So if temperature is held constant, and of course it goes without saying, it's assuming what else is held constant, number of particles. So if we double the pressure, now this is kind of hard to think. You can't really look at a gas and directly double its pressure. You have to do something to the gas to get the pressure to double. Now in this case, what it's saying is, what would you have to do to the volume to get the pressure to double? Well, based on what we know about gases, if you squeeze a gas down to a smaller volume, the pressure is going to increase. If you stretch that container out and increase the volume of that container, the pressure is going to decrease. So in this case, if I want to double my pressure, I'm going to have to squeeze that container to half the size. So 450.0 milliliters. Cut down half the size, divided by 2, that's going to give me 225.0 milliliters. 4 sig figs. Okay? So that's letter A. For letter B, if I want it to be reduced to 1/4, if I want the pressure to go down, what do I have to do to the container or the volume? make it go bigger. So if it's going to go down to 1/4, I have to quadruple the size of my container. So it's going to be 450.0 times 4 times 4. So times 2 would be 900. So times 4 is going to be 1800. Now with sig figs, 4 sig figs, how do I show this with 4? Add a point at the end. Or technically 1.800 times 10 to the third. Okay. Number 27. A sample of oxygen that occupies 1.00 times 10 to the 6 milliliters at that pressure is subjected to this pressure. What will the final volume be if temperature is held constant? And of course, it doesn't say it, but we have to assume that number of particles is constant too. So let's write down what we know. That's the initial starting volume. Well, I'll write it this way. V1, initial volume, is 1.00 times 10 to the 6th milliliters, which really is a million with 3 sig figs. Million? Yeah, million. Initial pressure, P1, is 575 mmHg. The new pressure, P2, is going to be 1.25 atm. Now here's the problem. I'm going to end up dividing one of these by the other one. You can't divide mmHg by atm, so we're going to have to do a conversion here. Now it doesn't matter which one you choose. The units are going to cancel anyway. We have to either turn the mmHg into atm or vice versa. Let's just choose to turn the atm into mmHg. Doesn't matter which way you go. So 1.25 atm times 760 mmHg per 1 atm, or equals 1 atm. This gives us 950 mmHg. Okay? So now my pressure units are the same. We're good. If you turn that into atm, it's fine that way too. And we're solving for the new volume, so that's going to be my question mark. Okay? So P1 V1 over T1 equals P2 V2 over T2. Temperature is held constant, number of moles as well, so let's get rid of this. We're solving for the new volume, solve for V2. So V2 is going to equal, let's get P2 out of here, P1 V1 over P2, which is going to be my starting pressure, 575 mmHg, times my starting volume, which is 1.00 times 10 to the 6 milliliters. 10 to the 6th milliliters. Divided by my new pressure, which is 950 mmHg. Now, hopefully at this point, if you forgot to convert the pressures to the same unit, you would catch that mistake, because you wouldn't be able to cancel. You would see two different units here. But in this case, it works. Milliliters is my last unit. Does that make sense for volume? Yes, it does. Let's solve. 575 times 1.00 E6, or just times a million, divided by 950 equals, my calculator gave me a really big number. Let's look at sig figs here. 3 sig figs, 3 sig figs, 3 sig figs. I'm going to write 605,000. And my unit is milliliters. 3 sig figs. Okay? Let's take 15 seconds and see, does this make sense? So it started at 1 million milliliters with this pressure, which, at 575 mmHg of pressure. It then turned into this pressure, which we worked out to be 950. So it went from 575 to 950, so the pressure went up. What must you do to a gas to make its pressure go up? What must you do to the volume? Well, you have to squeeze that container smaller. So does it make sense that it went from 1 million to 605,000? Yes, it does. We can move on. 28. To what temperature? Right away, T2 equals question mark. Must a sample of nitrogen at 27 degrees Celsius, that's going to be T1. Now right away, what are you going to have to do to that? Kelvin. We add 273 to this. I've made way too many mistakes adding this number. I'm going to do it on my calculator. 27 plus 273 gives me 300. But really, this isn't to the nearest whole number, so I'm going to add a point at the end. And again, if you added 273.15, you would get 300.15, but you'd cut that 0.15 off anyway. So you may as well just add 273. 0.625 ATM is my starting pressure. P1 equals 0.625 ATM. Okay, and my new pressure, so it's going to become P2 equals 1.125 ATM. At constant volume, volume is held constant, and of course it doesn't say it here, but number of particles is also going to be held constant. So to what temperature? We're solving for T2. P1 V1 over T1 equals P2 V2 over T2. Let's get rid of what we can cancel right away. V2 goes away. Yeah, constant volume. V2 goes away. V1 goes away. This is my formula. Now we're solving for T2. T2 is by far the most difficult of the 6 letters to solve for. I see people try to do this in one shot and get it wrong. Often what people would say is this. Let me divide both sides by P2 to get this out of here. So P2 goes away and reappears down here. And then they say P1 over T1, P2 equals T2. But that's not correct, because technically, if you divide by P2, you're not left with T2. You're left with 1 over T2. So technically, you could just reciprocate both of those, flip them. But the best way to do it is this. Starting from this, you say, I hate denominators. What can I do to get this out of the denominator? Well, multiply both sides by T2. Let's multiply by T2. It's going to disappear from down here, and it's going to reappear up here. Okay? Now, I still have this denominator. I still hate denominators. Let's get that out of here. So T1 is going to go away. You're going to multiply both sides by T1, and it's going to reappear up here. And now, if I showed you that and said how to get T2 by itself, you should be able to easily tell me. Divide both sides by P1. P1 goes away over here, and that's T2. Let's solve. So P2 is going to be 1.125 ATM times T1, which is 300 Kelvin, divided by P1, which is 0.625 ATM. ATM cancels ATM. My unit is Kelvin. Does that make sense for T2? Yes, it does. 1.125 times 300 equals, divided by 0.625 equals, final answer of 540 Kelvin. Now, let's check our sig figs here. It's very easy. Common mistake. People will look at the problem and say 2 sig figs, 3 sig figs, 4 sig figs. I'm going to use 2 sig figs. But did we ever actually plug 27 into the problem? No. We took our temperatures in Celsius and converted them to Kelvin. We didn't plug in 27. We plugged in 300 point. So you use the Kelvin temperature, not the Celsius temperature, to determine your significant figures. In this case, we have 4 sig figs, 3 sig figs, 3 sig figs. I'm going to use 3 sig figs. How do I do it? Add a point at the end, and that's my answer in Kelvin. The problem asks to what temperature. It doesn't ask for it in Celsius, so technically we can leave it like this. But let's turn it back to Celsius just to see what it's going to be. So when you go from Celsius to Kelvin, you add 273.15. So when you go from Kelvin to Celsius, you do the opposite. Let's subtract 273. I don't even need to do the 0.15 because it's going to get canceled anyway. 540 divided minus 273 gives me 267 degrees Celsius. Okay, so that's number 28. Sheet here. Good. 29. A gas has a volume of 1.75 liters. V1 equals 1.75 liters. At negative 23 degrees Celsius, T1 equals negative 23 degrees Celsius. Right away, let's turn that into Kelvin. Negative 23 plus 273 gives us 250. Now, I'm not going to leave that as 250. I'm going to add the point there because I know it's nearest whole number, nearest whole number. And the initial pressure, P1, is 150.0 kilopascals. At what temperature? T2 equals question mark. At what temperature? In degrees Celsius, which we're going to have to turn that into Celsius at the end. What I see a lot of people do is say, oh look, it's asking for Celsius. So we're going to have to leave T1 as Celsius to get it in Celsius. Cannot do that. You can't plug Celsius into the combined gas law. So what we're going to have to do is solve using Kelvin, and then at the end, go back to Celsius. So that's our variable we're looking for. Would the gas occupy at a new volume, V2 equals 1.30 liters, and a new pressure, P2 is 210.0 kilopascals. So this is that second type of problem I mentioned. Nothing's held constant here, except of course, number of particles. Just doesn't mention anything about that. But we have nothing else constant. We're changing the volume and we're changing the pressure and we're saying what's the new temperature going to be. So I give you 5 variables, you solve for the 6th. P1 V1 over T1 equals P2 V2 over T2. We're solving for T2. Again, difficult. Be careful. First thing, I hate denominators. How do I get T2 out of the denominator? Multiply it by both sides. It goes away over here and it reappears up here. How do I get T1 out of here? Multiply it by both sides. Or multiply both sides by T1. It's going to reappear up here. And now it's easy to get T2 by itself. Divide both sides by P1 V1. It cancels over here. And it reappears over here. Let's plug in our values. Definitely want to include the units here. A lot of mistakes can be avoided if you use your units. It takes you an extra 10 seconds, but it's going to be worth it. So T2 is going to equal P2, which is 210.0 kilopascals. V2, which is 1.30 liters. T1, 250 point Kelvin. Divided by P1, 150.0 kilopascals. Kilopascals, lowercase k. And divided by V1, which is 1.75 liters. Let's check our units. Kilopascals cancels kilopascals. Liters cancels liters. What's left? Kelvin. Does that make sense for T2? Yes, it does. 210.0 times 1.30 equals, times 250 equals, divided by 150 equals, divided by 1.75 equals, and the answer I get for T2 is 260 Kelvin. Now, for sig figs, I'm not going to look at this and say 2 sig figs, because I didn't plug negative 23 in, did I? No. I turned that into 250 and plugged that in. 250 point, I should say. So 4 sig figs, 3 sig figs, 3 sig figs, 4 sig figs, 3 sig figs, 3 sig figs. My answer is 260 point Kelvin, but the problem asks for Celsius. So we're going to take this and we're going to subtract 273, and we're going to get negative 13 degrees Celsius. Now, why don't I keep 3 sig figs? Because I'm not multiplying or dividing, I'm subtracting. So nearest whole number, nearest whole number. My answer is negative 13 degrees Celsius. I think I forgot to check in the last problem. Doesn't make sense, but we'll just move on here. But for this type of problem, sometimes it's difficult to see if it makes sense or not, because we're changing 2 things. Now, if those 2 things have the same effect, it's easy to see if you got the answer right. If those 2 things have opposite effects, you have to see which one's going to have more of an effect. It's hard to tell. But let's check this one. What did my volume do? My volume went from 1.75 to 1.30, so it shrank down. Now, this one's tough to visualize in your head. If you shrink a gas down, what's its temperature going to do? It's hard to imagine that, but temperature should go up in theory. So does it make sense that, yeah, we went from negative 23 to negative 13, so it did go up. And second, for pressure, my pressure here, 150 went to 210, so my pressure went up, temperature should go up, let's see, hold on. Pressure went up, temperature should have gone up, which it did. Again, these are a lot more difficult to visualize because, especially when you're solving for T2, but because sometimes those forces go in opposite directions, okay? So we'll just kind of leave it at that. This does make sense. Check your math and see, does it make sense that each of those affected it? Number 30. A gas at this pressure, in pascals, and this temperature in Celsius. Let's go ahead and write those down. P1 is 7.75 times 10 to the 4th pascals. T1 is 17 degrees Celsius. Right away, let's turn this into Kelvin. 17 plus 273, 290 point Kelvin. Occupies an initial volume V1 of 850.0 centimeters cubed. At what temperature? Again, we're going to solve for T2. In degrees Celsius, would the gas occupy at V2 equals 720.0 centimeters cubed? And P2 equals 8.10 times 10 to the 4th pascals. So it's basically the same as last problem. P1 V1 over T1 equals P2 V2 over T2. Let's get rid of this denominator by getting rid of that and putting T2 up here. Let's do the same. Let's get T1 up here by multiplying. That gets rid of both my denominators. Now to get T2 by itself, I simply divide both sides by P1 V1. This goes away, and that's my equation. That's a 2 there. Okay. So T2 is going to equal my P2, which is 8.10 times 10 to the 4th pascals. V2 is 720.0 centimeters cubed. T1 is my initial temperature, 290 point Kelvin, divided by P1, which is my initial pressure of 7.75 times 10 to the 4th pascals, divided by V1, which is 850.0 centimeters cubed. Let's see if my units make sense. Pascal cancels Pascal. Centimeter cubed cancels centimeter cubed. I'm left with Kelvin. Does that make sense for T2? Yes, it does. Let's solve. 8.10 E4 equals times 720 equals times 290 equals divided by, be careful here, if you use E, you will be fine. If you don't use E and you divide by this, you can't just say divided by 7.75 times 10 to the 4th, because your calculator thinks in PEMDAS and it's going to get it wrong. If you put this in parentheses, you're okay. Or if you use E, you're okay. So be careful. Divided by 7.75 E4 equals, divided by 850 equals. And I get a value of T2 equal to 3 sig figs, 4 sig figs, 3 sig figs, because of the point, 3 sig figs, 257 Kelvin. We have to answer in Celsius though, so minus 273 Kelvin gives me negative 16. Let's see if that's what I got on my answer here. This is 30. Yep, negative 16 degrees Celsius. Okay. 31. A meteorological balloon contains 250.0 liters of helium. That's going to be the initial volume of this balloon. V1 equals 250.0 liters. At 22 degrees Celsius, that's my initial temperature. Right away, let's turn that into Kelvin. So I've made way too many mistakes doing this in my head. 295 Kelvin. 740.0 mmHg is P1. If the volume of the balloon can vary according to external conditions, in other words, flexible container, what volume would it occupy, V2 equals question mark, at an altitude at which temperature is T2 equals negative 52 degrees Celsius, negative 52, plus 273 is 221 Kelvin, and the pressure is 0.750 atm. P2 equals 0.750 atm. Do you notice the problem? P1, P2, they don't have the same units. We're going to have to turn one into the other. Now last time we turned my atm into mmHg. Let's do it the other way. It doesn't matter. oh, no, not this way. Let's do it this way. So my mmHg times 1 ATM over 760 mmHg, 740 divided by 760 equals 0.97, no, I see 4 sig figs here, 9737 ATM. Okay? This is one of these weather balloon questions. It's kind of a classic chemistry question. It's hard to think about because as the balloon goes up, it's colder, which means the balloon should shrink. But the pressure up there is also much less, which means the balloon should grow. So there are two counteracting forces. Is the coldness of it going to make the balloon shrink, or is the low pressure of it going to make the balloon grow? Let's see. So we're solving for V2. This should be a little easier than T2. P1 V1 over T1 equals P2 V2 over T2. Let's get let's get V2 by itself. T2 is going to reappear up here. And now we're getting V2 by itself. Let's divide both sides by P2 to get that out of here. And that's my equation. Let's plug it in down here. T2 is 295 Kelvin. P1, 0.9737 ATM. V1, 250.0 liters divided by P2, which is 0.750 ATM, divided by T1, which is 295 Kelvin. Now, hopefully at this point, if you forgot to do the conversion of your pressure units, you would notice ATM, mmHg, and you would say, wait, I need to do that. So, Kelvin cancels Kelvin. ATM cancels ATM. We're left with liters. Does that make sense for V2? Yes, it does. Let's see what we get. 295 times 0.9737 equals, times 250 equals, divided by 0.750 equals, divided by 295 equals, a final volume V2 of 324.56666. Let's check sig figs. 3 sig figs, 4 sig figs, 4 sig figs, 3 sig figs, 3 sig figs. Again, don't be thrown off by the fact that we use 2 sig figs here and 2 sig figs here, because did you actually use 22 and negative 52 in your equation? No. You used the Kelvin version. So with 3 sig figs, my answer is going to be 325, and my unit is liters. Okay. Let me check my answer key. I got a different answer. Where did I mess up? Let's see. I either mess up my answer key or I mess this up. Let's see. First of all, let's see if I rearranged correctly. So P1 V1 over T1 equals P2 V2 over T2. V2 is trying to isolate, so T2 P1 V1, T2 P1 V1, divided by T1 P2. Okay, so the formula is correct. All right, there it is. Hopefully you caught this mistake. I should have used T2 here. Notice I used T1. See, this is that point where I probably would have restarted the video if I weren't already half an hour into it. All right, 295 goes away. This should be T2, which is 221. Notice I used the same temperature. I should have caught that. T1 is correct down here. T2 is correct up there. Let's do this again. 221 times 0.9737 equals, times 250 equals, divided by 0.750 equals, divided by 295 equals, with 3 sig figs, 243 liters. That's correct according to my answer. Good. All right. Number 32. The balloon in the previous problem will burst if its volume reaches 400.00 liters. Given the initial conditions specified in that problem. So the initial is like the 111. Let's record those same as before. V1 is 250.0 liters. T1 is 295 Kelvin. P1 is 0.9737 ATM. Now actually, I happen to get lucky because notice this final pressure is given in ATM too, so I would have had to do the math again to change it after. Anyway, I have my initial conditions. Okay, given the initial conditions, determine at what temperature in degrees Celsius. So we're solving for T2. The balloon will burst if its pressure at that bursting point, if P2 when it bursts is 0.475 ATM. That's what I meant when I said I got lucky. I chose the right one to flip because we now have ATM. So really the 400 there, that's going to be my new volume. Because it says when it gets to that point, what's the temperature going to be? So 400 liters, 400.0 liters is going to be V2. Okay? So we're solving for T2 again. We've done this plenty of times. T2 equals, well, let's start from scratch again. P1 V1 over T1 is P2 V2 over T2. T2 is going to go up here. T1 is going to go up here. That gets rid of my denominators. Divide both sides by P1 V1. So it's, I'll do it over here. Divided by P1 V1. This cancels. And this is what I get. Okay? T2 is going to equal P2. Let me be really careful here. 0.475 ATM. V2, 400.0 liters. T1, 295 Kelvin. Divided by P1, 0.9737 ATM. Divided by V1, 250.0 liters. ATM cancels ATM. Liter cancels liter. I'm left with Kelvin. Does that make sense for a T2? Yes, it does. Let's solve. 0.475 times 400 equals, times 295 equals, divided by 0.9737 equals, divided by 250 equals, check our sig figs. 3, 4, 3, 4, 4. 3 sig figs. Let's see what we get. My calculator says 230.255. I'm going to go with 230 Kelvin. Now the problem asks for degrees Celsius, so minus 273 gives us negative 42.7, well that's with my rounding here, negative 43. That's going to be the temperature. Okay? And that kind of makes sense. That's about how cold it is way up in the atmosphere. Last problem. This is probably beyond the scope of what you would expect to see on a Chem 1-2 test, but you should be able to answer this. It's basically a combined gas law problem combined with a conversion factor problem. The normal respiratory rate for a human being is 15.0 breaths per minute. The average volume of air for each breath is 505 centimeters cubed at 20.0 degrees Celsius and 9.95 times 10 to the 4th pascals. What's the volume of the air at STP that an individual breathes in one day? Give your answer in cubic meters. All right, so we're going to have to find two things here. We're going to have to find the volume of one breath, not at these conditions, it's already given. In those conditions, we're going to need the volume of one breath at STP. And then we're going to need to figure out, well, if that's one breath, if you breathe 15 times a minute all day, what's the total volume going to be? So let's start with converting 505 centimeters at this condition and that condition to see what the new volume would be at STP. So essentially we're solving for V2 using these initial conditions. So V1 is 505 centimeters cubed. T1 is 20.0 degrees Celsius. Notice, I can't just add 273 anymore because I added 0.0. So I'm going to add 273.15. This I can actually try in my head. Plus 20, 293. 293.15. Since I have one decimal point, it's going to round off to 0.2. So that's really what I should be recording here. 9.95 times 10 to the fourth pascals, that's going to be my initial pressure. 9.95 times 10 to the fourth pascals. I'm going to say, what's the new volume going to be, V2 equals question mark, at STP? Well, what does STP tell me? That tells me my T, which is T2, and it tells me my P, which is P2. So T2 is going to be standard temperature, which is 273.15 Kelvin. P2 is going to be standard pressure, which I can write 1 atm or 760 torr or 760 mmHg. But let's be smart about this. What's my initial pressure unit? Pascals. I may as well write P2 as STP in pascals, if you know that. So it's going to be 101,325 pascals. Now, you can write 1 atm here. It just means you're going to have to convert this to atm, or you're going to have to convert that to pascals anyway. So these are my conditions. Let's solve for V2, and that's going to tell us what one breath is going to be at STP. P1 V1 over T1 equals P2 V2 over T2. V2, to get this by itself, first thing we do is multiply both sides by T2. Let's get this up here. Now, to get V2 by itself, multiply both sides by, divide both sides by P2, get this out of here, and that's going to reappear down here. So, V2 is going to equal this, so let's plug it in carefully. T2 is 273.15 Kelvin. P1 is 9.95 times 10 to the fourth pascals. V1, initial volume, 505 centimeters cubed, divided by my new pressure, which is 101,325 pascals. That's 101,000. And divided by T1, initial temperature, 293.2 Kelvin. Let's see. Kelvin cancels Kelvin. Pascal cancels Pascal. I'm left with centimeter cubed. Does that make sense for V2? Yes, it does. Let's see what we get. 273.15 times 9.95 E4 equals times 505 equals divided by 101,325 equals divided by 293.15 equals 5 sig figs, 3 sig figs, 3 sig figs, 6 sig figs, technically infinite sig figs, and 4 sig figs. 3 sig figs, V2 equals 462 milliliters. What does that represent? That's what one breath would be at STP. Okay? We're almost ready to solve the problem. I'm going to try to squeeze it in here if I can. That's going to be too tight. So we're looking for how many of these breaths you're going to take in one day. We're starting with 15.0 breaths per minute. 15.0 breaths per minute. Let's convert this into breaths per day. Well, how many minutes in a day? I don't know, but I do know how many minutes in an hour. 60 minutes per hour. Cancel, cancel. And I know how many hours are in a day. Hour, hour. Now, if I just solve this out, it's going to give me how many breaths in a day. And then I can multiply those number of breaths by the volume. But let's just tack on a conversion factor and do that all in one step. I already worked out a conversion. This is one breath. So one breath at STP equals 462 milliliters. Let's just work that out right now. Times 462 milliliters per breath. Where did I get milliliters from? I subconsciously knew centimeters cubed equals milliliters, so I wrote that. Sorry. I mean, it's the same thing. Technically, it's not wrong. It's just weird that I converted that. Centimeters cubed. Breath cancels breath. So that's now the volume of a whole day's worth of breathing at STP. Now, if you solve that, what's your unit going to be? centimeters cubed. It's going to be a giant number of centimeters cubed. But we're not looking for centimeters cubed. We're looking for meters cubed. So another great opportunity to utilize a conversion factor. We may as well tack on at the end here. How do I go from centimeters cubed to meters cubed? Well, you go 1 meter over 100 centimeters cubed, or as I prefer to do it, write it 3 times. So in this case, centimeter cubed cancels centimeter, centimeter, centimeter. I'm left with meter, 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 meters cubed. This works out. Let's see what we get. 15 breaths times 60 minutes per hour times 24 hours per day times 462 centimeters cubed per breath divided by 100 equals, divided by 100 equals, divided by 100 equals, and with how many sig figs? 3 for my starting. Infinite sig figs, 3 sig figs, infinite sig figs, infinite sig figs, infinite sig figs. With 3 sig figs, I get a final answer of 9.98 meters cubed. That's the volume of breath that you're going to breathe in a day at STP. Okay, that's the end.